me if you can see that. I'm going to put it on presentation mode.
Yes, we can see that.
Okay, great. All right, so this is a modern X-ray system for the small angle X-ray scattering system that does SAXS to wax on one platform. But it's very similar to what you have now. It's just a newer version with more automation and newer components that kept more or less up to date with the current times. I'd say there was a big change in what we can do within the past 10 years. The most substantial change has been in the detector technology, and you have one of those types of detectors now. We'll talk a little bit about that later. So let me just give you a brief introduction on Xenocs, because a lot of people have not heard about us. We are basically a group of scientists and engineers, about 100 people now worldwide. The headquarters are based in Grenoble, France, right across the street from the ESRF, the European Synchrotron Source. And I would say that a lot of us are, forming this sort of confederation under the Xenocs umbrella of people who have worked in small angle scattering for much of their career. This is the new headquarters in France. It really is a lovely building, brand new. And this is our headquarters in the US. This is in Holyoke, Massachusetts. I actually love this building. It's an old mill building where, because Holyoke is one of the textile manufacturing centers in the US in the, starting with the Industrial Revolution. And you'll notice water surrounding the building. Those are canals diverted from the Connecticut River. The building has its own hydroelectric generator, about 100 years old. So we generate our own electricity for use in the building. And we are in the basement space of the unit that you see on the left-hand side. So let me give you an idea of small angle scattering just in a quick snapshot. This is our measurement space, and the idea is that we can see, and I'll use that term loosely, we can see or probe structures that have size dimensions that go all the way from atomic structure, which we measure in wide angle X-ray scattering, all the way to features that are a micron in size. So this is a tremendous 4-order magnitude of, or more of spatial dimensions that we can probe with a single X-ray platform. Most of the time when we talk about SAXS, we're really working in this 10 to 100 nanometer range. And I'll be switching back. My instinct is to talk in angstroms. I'm trying really hard to work in nanometers, but just forgive me if I slip. I usually think in angstroms because that's sort of the natural unit that we use for scattering. So we're going to see things that have applications in micelles, proteins, mostly polymers, but now we can start touching viruses and grain boundaries in larger scale structures using specialized techniques like ultraSAXS. So in order to appreciate how SAXS makes its measurement, let's go back to the basics. This is just a slide giving a picture of Bragg's law, n lambda, where lambda is wavelength, and n is just an integer. So we could just let n equal 1. Lambda equals 2d sine theta. D is the spacing between atomic planes, and theta is our scattering angle. It's defined here. Let me see if I can get a pointer. And then theta is our scattering angle here. So this is Bragg's law. It's something that we've all seen in introductory chemistry or first year chemistry, first year physics. And what it tells us is that when we scatter X-rays from a crystal, we get constructive interference when the theta is such that we get constructive interference between atomic planes, and that leads to seeing discrete peaks in the intensity, the scattered intensity, as a function of the scattering angle theta. Well, we can generalize this a bit. And the generalization when we talk about scattering as opposed to diffraction is we use this so-called Laue-Ewald construction, but just look at what's on the right-hand side. We can reformulate Bragg's law by defining something called a momentum transfer scattering vector Q as 4 pi sine theta over lambda. These are all the elements of Bragg's law. And then we can make a very simple relationship between this factor of Q and the D spacing of the, let's say in Bragg's law, it was atomic layers, but it could just as well be the size of a particle or the distance between particles. So we're going to always go back to this very simple relationship, and we will always use this Q as our independent variable. So rather than plot intensity as a function of angle, we're always going to plot it as a function of Q. And I'll reinforce this as we move along. So just some housekeeping. The scattering vector Q is also called the momentum transfer scattering vector. It has the dimensions of inverse length. And so when we talk about scattering, it's a function of Q, and that scattering intensity is measured in so-called reciprocal space or Q space. And of course, the opposite of that is inverse Q, which is real space. So now we can make this conceptual leap from scattering from atomic planes to scattering from a single particle. And you can appreciate that if we have an incoming beam of X-rays and they scatter off from one end of the particle and the other side of the particle, they scattered into an scattering angle 2 theta. If I define Q by the conventional way we did, I should see a constructive interference when the Q is equal to 2 pi over the diameter of the particle. And of course, we can do a calculation. You'll see data later where you see oscillations in the scattering intensity. But what one sees is that there is constructive interference scattering from, this is a calculation, but it's scattering, showing scattering from spherical particles. And the distance, the separation in Q between maxima or minima is just 2 pi over the diameter of the particle. So notice that when you go from a 100 angstrom particle to a 200 angstrom particle, as the particle size gets bigger, these oscillations, these peak maxima and minima distances compress. And that's consistent with Q being inversely proportional to the spatial dimension of what you're looking at. So how do we set up experiment? SAXS experiment is almost self-defined, small angle X-ray scattering. We have an X-ray source. We make the X-ray source monochromatic. That is, it usually has a distinct characteristic X-ray line. For most laboratory sources, we use a copper X-ray source. It has a wavelength of 1.5 angstroms or an energy of 8 kilovolts. That X-ray source is coupled to a monochromator optic, which also focuses the beam and tightens up the intensity as we pass through a set of collimators. And these are just literal slits that define the angular divergence of the beam as it goes through the sample. And then we measure the scattering on a 2-dimensional area detector scattered into an angle of 2 theta. And we get a 2-dimensional image of the scattering all around the azimuthal angle that are defined going around like this, from 0 to 360 degrees. And of course, we measure intensity as a function of Q, and Q, once again, is related to 2 pi over the D space. So we can think about this as the D as our probe length. So when we change Q, when we look at the scattering intensity as a function of Q, Q becomes our little dial. We can look at the different scattering angles and pull out from that a probe length scale that we're looking at. So unit conventions, as I said, Most of us still use reciprocal angstroms to express Q, but I think if we looked at international standards, it would still be reciprocal nanometers. You just have to pay attention and note which units people are using, because it's easy to get confused and be off just conceptually by a factor of 10 as you're reading a paper. Okay, the angular range of SAXS, I usually think about small angle scattering as when the scattering angle theta is sine theta is approximately equal to theta, but basically we're looking at things in the range of greater than 8 angstroms. On the other hand, you know, these are sort of artificial distinctions because most instruments can measure most SAXS instruments can measure continuously from SAXS to wax. This is what an image looks like, and this is what similar to what you'll see on what you would see on the current instrument at Colorado State. The image on the left is the two-dimensional area detector showing scattering rings from a sample that the X-rays have been transmitted through. So this is a transmission experiment. I'm just sitting there with a stationary detector, just letting the intensity accumulate, and it's forming rings. That tells me that the sample is isotropic. That is, there's no preferred orientation in the sample. It could be a solution or some sort of suspension. And then what we do is we integrate the scattering intensity going around the azimuthal angle from 0 to 360 degrees. Those places where we're missing data, we just ignore, but we don't count in the azimuthal averaging. And what we get is we make this 2D function, this 2D image, into a one-dimensional function of intensity versus Q. And I just want to point out a few features in this. Remember, again, we can relate the Q to a spatial probe length D, and you can see a peak that is occurring at 9 nanometers. So at 90 angstroms, we're seeing some sort of structure. And what this, I know what this sample is. It's a multilamellar bilayer. So what we're seeing is the characteristic bilayer spacing with some internal structure and higher harmonics occurring as we move out to larger Q. This bit here, which is a very large, this is on a log-log plot, this bit is the direct beam. So what you'll notice that's unusual about this picture is that if you've done scattering, you're probably used to having a beam stop to block the direct beam intensity. In this case, we are letting the direct beam intensity hit the detector, and this is basically our resolution function. So it doesn't give us any particular knowledge about the structure of the sample we're looking at, but it does give us the resolution function, and it does tell us what the transmitted intensity is. So we can use this to reduce the data to absolute scattering units, and if we need to, we can use this direct beam resolution function to convolute when we do any type of quantitative fitting to the scattering data. So let me just explore a little bit more about this. I keep on going back to this 2 pi over Q as a probe length. So we can imagine that at small q, in other words, very close to the direct beam at the smallest possible scattering angles, if we have particles in solution, imagine that at the smallest q, it's like we're looking at all the particles from a distance, and we're not seeing really anything about their specific details of their structure. For all intents and purposes, we can just consider them to be like spherical blobs. But we can say something about their average size just from the small q measurement. As we increase the scattering angle and increase q, we start looking inside those particles. So if there is, say, a phase separated structure within each of these particles that it's occurring at a large scale length, like maybe 100 angstroms or so, we're going to see that we're going to see a scattering signature due to that. And of course, as we keep on increasing the angle, we're going to get to wide angle scattering, where we're going to get information about chemical bond details. So as we move from high to low angle, high Q to low Q, we're more or less coarse graining the structure. So at lowest Q, we don't see all these internal details, but we can get average properties of the material. And again, scattering is hierarchical. What's really great about these scattering tools, where we'll consider it in the weak scattering regime, our building block is the scattering from the single electron. And then we put all those electrons together, they form an atom, and that gives us a scattering amplitude of the electron times the scattering factor for the atom. And then we can put all those atoms together into a molecule. And then we can put all those molecules together into a crystal. And then finally, we can take that crystal and we can build up our own little nanoparticle, at which point the summation over all the different components becomes an integral, because we've washed away the details of discrete atoms in the system. And then we can take these nanoparticles and we can start the process all over again. We can take these nanoparticles and use the scattering for the single nanoparticle and build up a crystal of nanoparticles if we want. So again, it's hierarchical. It's a simple, everything is a simple product of each of the components as we build up the structure. And you'll notice these are, you'll notice the Fourier transform term. These are the phase factors, basically the parts which cause all the interference in the scattering. We won't go into that too much this time. That'll be another talk in the future. So I just want to make it clear that when we measure the scattering, what we're actually measuring is these amplitudes in the modulus square. So we keep the magnitude, but we lose all the phase factor information. That's why we can't just look at the scattering pattern and Fourier transform it back to get a real space density distribution. But again, it's all about electron density. All right, so let's look at some examples. So this is a really current application. This experiment, this was done in the laboratory by a group at NIST that has and University of Maryland that have a biotech center. When COVID started, the only people who were in the building were the person who was running the SAXS instrument and the person running a cryo-EM. And what you can see here is this is solution scattering of the spike protein, showing the first Wuhan variant in this upper green curve, and the lower curve is the European variant. And this was done just a couple of months after COVID, after the Wuhan variant was established. So this doesn't look like a big change in intensity as a function of scattering vector, but for a SAXS, this is huge. This is a big measurable distance and would correspond to a structural change in the spike protein. So what this group did was they worked together. The cryo-EM group determined the electron density and the shape of the spike protein. And then this spike protein was used to decorate a polysorbate 80 particle as a vaccine. And this, in fact, is the Novavax vaccine that was developed using these tools. And what they could see in TEM data was this spike protein decorated the polysorbate 80 nanoparticle like a little rosette. But in fact, that's not what is injected into people. So they looked at it in solution with small angle X-ray scattering in the lab, and they found a very different structure that was consistent with the scattering data. And eventually they found the spike protein, maybe 4, 5, 6 spike proteins, decorating almost like a worm-like particle, nanoparticle of polysorbate 80. So this is really interesting. It's important because SAXS was the only tool that was able to show them what actually got injected. But they required that prior knowledge of the spike protein structure in order to finish the calculation. So the nice thing about SAXS is if you know what you have, you can calculate the scattering and compare it quantitatively to whatever you measure in the lab. Probably 90, I'll say at this point, 85% of what people look at in the laboratory is phase identification. And the most common example is seen in block copolymers, allotropic liquid crystals, and lipids, where they go through a series of ordered transitions. They can, of course, be disordered, but typically ordered transitions would be a lamellar phase, a hexagonal phase of rod-like nanoparticles, and a cubic phase with different particular symmetries. And then, of course, there are some more exotic phases that have been seen in all these different systems. So, for example, this is a case where a phase transition was seen between a hexagonal antimicrobial compound that broke apart and would form and would reassociate into a non-active, inactive hexagonal phase. I'm sorry, inactive cubic phase. So we see a transition going from hexagonal, where it's microbial active, to an inactive phase once it gets into the body. And this is actually fairly easy to index. And I'll give you, I'm not being completely honest here, because these lower two data sets were taken at the synchrotron, and it's only the upper data set that was taken in the laboratory. But you can see for yourself that the data quality is quite comparable between the two. It's just that it takes longer to count in the lab rather than the synchrotron. Another example for drug delivery where this is a little bit more complicated. Again, you have these complicated structures, but now we have a mixture. And even with a mixture of two different phases, we can still tease apart based on the quality of the signal and the accurate positioning of the peaks. And then finally, for those who do this type of work, we have the more exotic phases, the Frank Casper phases, the A15, the quasi-crystals. These are also all determined in a laboratory system. A big application is also in nanoparticles. So let me just briefly show you. We measure scattering intensity. If we're looking at a series of a solution of nanoparticles or suspension of nanoparticles, we measure the X-ray scattering. We have some constant factor in front. This can be calculated. Then we have something called our form factor, which is the scattering for the individual particle. This is calculable for many different shapes and sizes. We usually just assume start off with a simple spherical assumption. And then finally, this term is an interference term, because remember, not only do we see the scattering from single particles, but if they come close together, we're going to see interference between the adjacent particles. Usually, we work in a solution that's dilute enough so this term can just go to 1, and we're just seeing the scattering due to basically isolated non-interacting particles. We'll look at some cases where we turn on this interaction and see the effect it has. So this is scattering from gold nanoparticles. We didn't even reduce this to absolute scattering units. I didn't care about the prefactors. I just used a general scale factor. But what you can see is this is the scattering. Remember, this part is our direct beam. It doesn't have any information about what's inside, the scattering from the sample. And we just looked at the first part of the scattering. These other peaks are artifacts due to the window material. But we can see that the green curve is calculated for spherical gold particles with this distribution, and the fit is really excellent. And I would say that the software that is available through that we have developed over the past few years is one of the things it is extremely robust for this type of data fitting without any requirement that the user go in and adjust parameters along the way. And this was spot on with what the expectation was for these particles based on prior knowledge. So I said before that when we look at smallest angle, we should be able to get information, simple information about the general size of a particle just by looking at the scattering at the very lowest angles. And in fact, we can by something called a Guinea approximation, which takes into account that I'm looking at a probe length much larger than the particle size, and I can just simply plot the log of scattering intensity as a function of q squared, get the slope, and that slope will give me the average radius size of that particle. Of course, this is complicated when you have polydispersity in the sample, but for narrow dispersity samples, this is an incredibly useful tool and will tell you whether things are not only reasonably monodispersed, but also if there's any sort of aggregation. And I won't go into that now, but what's also really cool about looking at scattering at the various lowest angles is that the inverse scattering length, right? If you're at low Q, the very lowest Q starts to 2 pi over that low Q starts to look like a macroscopic distance. So really we're measuring, we're sensitive to fluctuations in density of the system at those very lowest Q. And that's related to osmotic compressibility, which is really, we're doing thermodynamics when we look at the very lowest intensity at the very lowest scattering angles. And I think it's one of the most coolest things about scattering for me. And likewise, we can measure whether or not these nanoparticles, the very dilute phases, are repulsive with each other or attractive. And this has implications for drug delivery through nanoparticles, whether they're lipid particles or decorated polysorbate 80. It's important to work in a regime where they are repulsive with each other, and SAXS can tell us this so that they don't clump up when they're injected into the body. And then what happens when we turn on these interactions? This is a case where this P of Q is the individual particle, we'll call it the form factor. And as we increase the interactions, basically turn on the interactions between the particles, we get this additional IQ term, which we can relate to a particle-particle correlation function, identical to what we do with in the theory of liquids, simple liquids. And then when our particles are monodispersed, highly monodispersed, like a protein in solution, we can not only determine the size based on what we'll call it the low-hanging fruit from the Guinea plot that I referred to before, but we can in fact determine a priori model of the envelope shape of the protein in solution. And these are series of programs that have cloud access. If you have a monodispersed sample like a protein, these programs can be used in a cloud computing format. And then we have additional complications where we have the particle form factor. This is for another example where we turn on the interactions. This is the particle form factor for a bilayer. And then we have the structure factor, which describes the interactions between multi-lamellar bilayers. And then our scattering curve looks really wild. This is the intensity as a function of Q. But what's important, as I said before, is once you have a good model for, say, a bilayer, we can extract it from the scattering with a high degree of fidelity. These, I'll skip this if you are interested. This is DNA origami. This is from Oleg Gong's group at Brookhaven National Labs and Columbia University, where SAXS is used to determine the structure of a very, very beautiful and symmetric cage assembly constructed from individual strands of monodispersed DNA. And these can be decorated inside with either nanoparticles, quantum dots, or proteins. I'll skip this. This is just showing that we can determine particle size distributions. And I want to just bring home that we're often interested in changes. Of course, we're interested in structure, but we also want to see changes as a function of some external parameters. So this is a waterfall plot of a SAXS image and the wax scattering as a function of temperature. And these were all determined on a laboratory system. And you can see changes. The bright lines are basically diffraction peaks, scattering peaks. And you can see the change as we go from low to high temperature and back down to low temperature, and see the corresponding hysteresis. But these are typical experiments of what one would be able to do in the lab. And I believe you've got a Lincoln heater stage. These types of experiments are easily accessible to anyone on the system. And then finally, not all samples scatter isotropically as a function of this azimuthal angle, but we can of course see anisotropy. And it's important that we have this two-dimensional area detector so that we can actually see where the anisotropy is in the sample. And of course, these nice directional peaks correspond to the direction, in this case, of a stretched polyethylene sample. Finally, I should mention that you can do grazing incidence scattering. So this is a way to probe structure at a surface or in a thin film that might be too thin to scatter from using transmission small angle scattering. So this is a way to, if you will, to boost the scattering signal by looking at it in this grazing incidence geometry, where we can trap the X-rays in the surface of the material using basically X-ray optics by coming in below a critical angle for total reflection. And we can look at ordered films. We can look at disordered or partially ordered films. You can see this is the scattering, this is the sample plane, and we can see the scattering in the plane above. And then, as I said, we can move the beam stop away and see what's missing. So this is scattering from a sample. It's turned on its side, so that's why the scattering is going off to the right. Anyway, I can talk more about that if there are questions on GSAXS, but I'm pretty sure you have a GSAXS stage available to you on that system. I'll just mention the new systems. My hope, and I think this is shared by users at Colorado State, was that we did the upgrade of the detector to keep the system going for at least a couple more years, but eventually I think it's time to take advantage of the new developments in small angle scattering in the laboratory. That includes multiple X-ray sources, better collimation, more diverse sample environments, and finally that detector, which was stationary and outside of the vacuum chamber. Those detectors are now inside the vacuum chamber and run up and down on a rail system so that we can move continuously from SAXS with the detector back here all the way to wide angle scattering. This is shown here. So in this see-through, so we have a detector, we just give it a command to send the detector all the way back. We measure the SAXS, and then the detector can move all the way forward very close to the sample, and we can measure the wax. This is all done automatically. You basically set all your sample rack up, before you go home for the night. You say, okay, I want to run SAXS to wax on all these samples. You come back the next day, and all the data are collected. And then finally, we reduce the data in real time into absolute scattering units. So all those different sample to detector distances, the intensity is collected at all those distances. The intensity is integrated to make this one-dimensional curve, and all these different scattering curves fall on top of one another. So this is all different resolutions, 4 or 5 different sample to detector distances, and all the data fall on top of one another, all the way from SAXS to wax up to about 70 degrees and 2 theta. Sample chambers now are fairly large, so we can accommodate any number of different sample stages, temperature stages, shear stages, tensile, and the sample can also be isolated in air for those samples that can't go into the vacuum. We have heating stages, and I'm pretty sure you have the Lincoln temperature stage that's shown here. Lincoln also makes a tensile stage, which has tensile up to about 600 newtons in force, and it's actually improved since 20. It goes up to about 600 newtons and a temperature range of up to 350 degrees C. Temperature stage, the Lincoln stage, is how these waterfall experiments were done. The tensile stage, this is an example from one of our customers showing the SAXS development as a function of elongation of a composite. Actually, a polypropylene film. So I'm thinking of a different sample. Temperature control for multiple samples. These are accessible to you, not on the current system, but would be on a newer setup. Humidity chamber, this is available. This would fit into your existing cell. And this is an example of scattering intensity changes as a function of relative humidity at a fixed temperature. Room temperature samples for liquids, solids, gels. Grazing incidence stage with an additional rotation in the surface plane to pick up registry of, say, commensurate scattering registry with commensurate layers on top of let's say an etched silicon surface. And that's an example given on the right-hand side. That's silicon oxide, patterned silicon oxide on silicon. And then just for completeness, I'll show you a picture of a shear cell. We have different flavors to be able to do shear in situ while, and measure to measure the scattering intensity as a function of shear rate or quiescence after shear and relaxation. And this was a recent article. I'll make this available. You can look the article up. This was so many different. There were a lot of moving parts to this experiment, but the group at Sheffield, Sasha got this working beautifully all at the same time. Okay, I'm going to wrap up now. This is just virtual detector showing how once you have a detector in vacuum, you can move it around to collect a larger area than that defined by a single detector exposure. And of course, there's a GUI. I'm pretty sure, Brian, you can verify whether you have a GUI for experimental control that looks like this, but this makes it very easy for the user to just select out different setup parameters for a given experiment. I'll just skip through that. We have real-time imaging of the sample in the beam, so you can do a quick alignment just visually. And then we have a software suite, which I also believe you have, and verify that if you, Brian, if you have this or not. But this has the form factor fitting, particle sizing, etc. And it's comparable to SAS View if you've used that already. And it's always ongoing, an ongoing development. this is what I'd like to present if I had more time. I'd like to do a little bit deeper dive into some of the background of scattering and more examples of how to use, take advantage of all the information that's available, not just the peak positions or intensities. And then I'd like to just leave you with two references that I think are excellent. They're not exclusively small angle scattering. Each has a chapter in small angle scattering, but the background that they give you, especially this theory, this book by Sivia, will allow you to do that deep dive into the literature to understand what people are doing in more advanced applications. And the book by Jens Els Nielsen is basically a more advanced version of this book with more advanced examples. And with that, I'm going to say thank you, and I'd be open for any questions.
Questions from the chat?
Nope.
All right.
Hey, Scott, thank you very much. That was fantastic. This is Travis. I've been sort of monitoring the chat, and we have a couple of questions.
Okay.
Folks. And of course, they might be long, and I mean, you can figure out how to abbreviate your answer, right? One of the questions, I think, when you were talking about some of the single particle dilute scattering was, could you sort of give your impressions of how it compares to sort of the standard dynamic light scattering type measurements? And,
Yeah.
I'll give you a hint. The origin of this question may come, if Emma was going to ask. We teach a short class on structure and scattering where we introduce the students to DLS, and they do some measurements, and then they actually do that on the small angle X-ray system as well, and then they try to use FITs to extract information about particle size.
Mm-hmm.
And so I think sort of your perspective on the two techniques, and if you were to compare and contrast them.
Yeah, it's a really relevant question, and so the basic version is that when you do DLS, you're not actually measuring the particle, you're measuring the particle size with the hydrodynamic radius. That is, it's going to be close to the real particle size, but it's not actually going to be the particle size. You know, you would get a different answer if you did particle sizing with, say, even static light scattering, if the particle were big enough. The problem with looking at the DLS particle sizes is when you start to think that that is the actual size. What DLS is really great for is a quick measurement of something that gives me a metric that is related to size, at least has the dimensions of size, and also an idea of the distribution. The quality, of course, the quality is usually very high, the measurement is very fast, but it suffers when the particle is getting smaller and smaller. So, for example, and this is relevant for proteins in solution, you can see very subtle conformational changes that might lead to a dimensional difference that's on the order of maybe an angstrom in radius of gyration. You would not necessarily see that or should believe that from dynamic light scattering. But furthermore, remember that dynamic light scattering is only giving you that metric, that dimensional number. You can go back, as I showed on that protein slide, and determine the actual shape of that protein or its density distribution internally. We'll call that the pair density distribution function. That is going way beyond anything that you can do with a simple dynamic light scattering experiment. So I say you do both. You do the quick and dirty experiment with dynamic light scattering if you have it available. But then when you really want the details, you spend the longer period of time doing that careful measurement with small angle scattering to get not only a more accurate particle size, but to see what else is going on inside. And that's the really biggest difference. And then of course you have the situations where once you turn on particle-particle interactions, especially when you get to non-dilute solutions, then you're going to have a problem teasing out what the, even that even that size dimension from dynamic light scattering, because it really is a single particle scattering model. And you have to do several tricks like 3D DLS in order to really separate that single particle factor. And of course, opaque solutions are not opaque to SAXS, but are optically. So those are the basic differences. DLS has a place, an important place, and I look at both as really important tools.
That's fantastic. Oh, sorry. Thank you, Scott. It's fantastic. Actually, we sort of reiterate those things in my class or elements of that. So it's actually nice for someone else to confirm.
That's right. You're not crazy. It's real. Yeah.
Okay. Does anyone? I have one other question from the chat, but if we have another question from, I don't know if people want to put hands up. I don't see any of the participants. So I can see. Okay. So while we're maybe, but okay, I'll go ahead. Jacob has a question. It's about hierarchical structure and sort of the teasing out of different levels of order and structure. He says, I've grown polycrystalline polymer, a MOF inside a single large porous protein crystal. Can I use SAXS to quantify the size of the MOF crystals inside the protein crystal?
Yes. Yeah, and that's really cool. So the way that I would look at it, first of all, if they are totally different in dimensions, then it's easy, because for the protein you're going to see the there's a lot going on. If the protein is in a crystal, you're going to see the form factor for the protein. You're going to see, of course, the crystalline structure for the protein, and then you're going to see the MOF structure, which is going to be more or less look like a series of Bragg peaks. So yes, you will be able to tease them out, but to do that, you should look at the protein crystal first. It's you said it was semi-crystalline, so does that mean it would be isotropic, like almost like a powder pattern? You should characterize that with and without the MOF, and the difference will tell you what the contribution of the MOF is. And because they are probably going to be more or less discrete peaks, that should be straightforward. But of course, you have to try it. Yeah, but it's not a difficult experiment. It falls into the range of low angle. So on the current setup, you'd probably either want to remove some of the pipe or put it, I think you have 2 chambers, so you'd probably want to move it into move the sample into the second scattering chamber.
Yeah, it's great. And I have a little insight into this, but the protein crystal itself is actually an open hexagonal structure, I'm guessing. Is that correct?
Essentially a honeycomb, and the
MOF
is the honey.
Yes.
The way to
It's a honeycomb.
Oh, okay. Yeah.
So actually, there's multiple levels here. It'd be really cool to see it. Actually,
it would be that is a really cool experiment, and in my head, at least, what you described, given the size differential, it's almost a vanilla flavored experiment. If you have enough material, and the pores will scatter like crazy. The contrast between the pore, and especially if it's dry, if it's not hydrated, then it's even better.
Okay, let me see. Anyone from the audience have a question before I go back to the chat? Okay. This is from Nipa. How does peak intensity correspond with sample thickness? I have 1D data and 2D pattern of SAXS for my samples, which can be heterogeneous. I need to make a comparison between spots, okay, so intensity spot of the heterogeneous sample. What types of information are required to conduct absolute intensity calibration? It sounds like there's a series of things.
No, that's great. And we have a little, I think we have a little write-up on that, but it's actually in the, it's part of the data collection software that you can turn on the absolute reduction. So what's going to happen is the biggest thing that you have to be concerned about is, as you rightly said, is the sample absorption. So let's say you had a sample that did not absorb at all. Okay, so if it doesn't absorb at all, the thicker the sample, the higher the scattering peak. When you start to have absorption, what's going to happen is that scattering, of course, if it's infinitely thick, it's just going to be absorbed. If it's infinitely thin, then you're not going to see any scattering because there's not enough material. So what that means is that your scattering intensity is going to go through a maximum. So what we have to do is measure the transmitted intensity. And you could do that on this system, the system that's with the new detector at Colorado State, by simply doing the following experiment. You move the beams, this system has a beam stop because the detector is in air, but you can move the beam stop out of the way, measure the direct beam intensity, then put your sample in the beam, measure the transmission intensity, and the ratio will give you the transmission factor. That's the first thing that you need for accurately measuring the absolute scattering intensity. The other terms are geometrical terms that are based on the pixel size of the detector, the sample to detector distance, and the sample thickness. Well, those are all the known quantities, or at least you should be able to guess at the sample thickness if you can't measure it directly. So that's what goes into it. But yes, that's the secret sauce, is that transmitted intensity. So you're absolutely correct when you think that that's the crucial term, but it can be measured on the system, on that scattering platform.
So the procedure that Scott just went through is correct, but there's one button that you would press in the GUI to accomplish everything that he just said. So it's very straightforward and user-friendly to collect that kind of absolute intensity data on this system. Before you press the measurement, you just click the button that says you want to measure the direct beam. It will move the sample and the beam stop out of the way, measure and store that value, and then move your sample and the beam stop back and collect the data. So you already have all that information.
Good. Yeah, I didn't know what level of software you had, how automated that is. It's fully automated on all the, on most of, all of the new systems. And if you don't know the sample thickness, it will just, I think there's a default that it will just assume a 1 millimeter thickness just to keep everything, and you can scale it later when you know the sample thickness, if you don't think about it in the moment.
Okay, more from the chat. I'm sure you can see it, Scott, but that's okay. I'll let. So
Well, yeah. Oh, there's.
But don't worry about it. This is working great. Is it okay? From you to, is it possible to measure the change in crystallite size / orientation of a polycrystalline polymer while tension or shear forces are being applied?
Yes.
Yeah.
Yes. Yeah. I mean, if you want, so what you're going to see is, you're going to see, number one, you're going to see an anisotropy in the image. Say along, as you look along, and that anisotropy will be oriented along the principal axis of either the shear or the tensile stress, a tensile strain, and then in terms of crystallite size, you can estimate it from the breadth of the width of the peak of the crystalline peak, and you can also integrate over the do your azimuthal integration and integrate over the peak intensities and then the amorphous background to get percent crystallinity as well.
Hopefully that's good. Okay, last from Ojo. Can the SAXS, it's a tough one for you. Can
Yeah.
SAXS be used to study the profiles on passivated steel surfaces? We might need more detail on that, but
Yeah. So two things. So the short answer is you're going to see something. You're going to see something. You're going to see something, and it's a question of you're going to have a model in mind. But what you would see is the following: there are two different flavors of experiment to do. One is X-ray reflectivity, and that will give you a measure. It will give you, basically it's specular reflectivity. So you're going to angle in, and you measure the intensity at the identical angle coming out. And that reflectivity curve can be fit to a density profile, electron density profile from the vacuum into the sample. So that's one. So you can see the change that the passivated layer has in the uppermost portion, how it changes the electron density. That may be because it's got some oxide in there, so it's going to dilute the metal in that uppermost layer. And you would see that change. You would see that change in the electron density. So that's one. Then two, you could look at the off specular, because very often when we do things to metal surfaces, even they can start out perfectly smooth, although none is really perfectly smooth, but they can start off reasonably smooth. But then when you do passivation, oftentimes you can get you can introduce a surface roughness, and you're going to see that manifest itself in the off specular reflectivity. So that surface roughness is going to be basically take an incoming beam and make it go above and below what would normally be the specularly reflected peak. And then there's another one, and that's just doing grazing incidence. So scattering. So that would be not just looking what's happening in the plane, what we call the plane of reflection, but what's happening off to the sides. So if there is a structural change that is more or less crystalline, then you're going to see discrete scattering peaks off to the side, and you can index those to the structure at the surface. And if that's changing, you're going to see those changes from relative to the first structure. But yeah, something like steel is it's okay. The problem was when you start to increase the Z, the atomic number, those scatterers are the dominant feature, are going to be the dominant scatterers in the signal. So if you have a very light oxide layer, you may not see that. You would see just what the influence that it has on the iron, let's say, or the additives in the steel. Does that answer your question?
I'm guessing it's a fantastic answer. It's interesting. It's still true. I started off playing as a graduate student, thinking I was going to do thin films and reflectivity.
Yeah.
And I remember sort of vividly figuring out how, you have to model the electron density in order to then, and then fit it to real data. And it was very difficult to get around that process, right?
Yeah. And you know what, the models are, there are even standalone inversions now, but usually the simplest model is best. So you just do a stepwise function, that has, and just let the steps soften, and that usually can fit something pretty well and give you an idea.
We have Topaz, which is Bruker's proprietary software for working with things like this, and Leptos. So we have the software to model and look at the data as well. I will say that we don't have the GI SAXS stage, unfortunately.
Oh,
for
you're
our
building
system.
here. I thought
Um,
on the Brooker or on the SAXS?
On the SAXS, we do have the
Okay.
software. If we had the data, we could model it, but we don't have the stage to be able to collect it on our small angle system.
Scott,
know-
we originally talked about it and we had it in there, and then not too many people were using it at that time. I think we had, it existed, right? But there wasn't a lot of evidence that we could extract meaningful data.
I see. Okay. Okay. Yeah, it might be interesting if somebody, if somebody has the interest to just hook it up again and see, just see if there's anything there. Because the original detector would, there was a risk that it would wash out some of the structure, discrete peaks that one might see in a sample like this.
Okay, I have one other one. I think we may have kind of addressed this, but maybe you'll be able to read more into this. Is there an additional detector monitor to record the incident beam intensity? I think it's always just distraction, yeah.
Well, this is on the new one, you just press a button, it moves everything out of the way.
I thought it was incident on the sample itself, so I was thinking
gotcha.
it was through.
Yeah, it would be through the subtraction. Yep.
Yeah. Yeah, there's no like the old system, I think, had a photodiode embedded into the in the beam stop, because we always needed the beam stop in place. Now we don't need the beam, you can move the beam stop out of the way and just measure the direct beam. You do see some additional scattering from the window in front of the detector and from the exit window, but those are negligible compared to the direct beam. So that's why we can get away with it. And we assume that, over the course of the experiment, that the intensity from the source is not changing. And that's a really good approximate. I mean, that's a good, that is a good, estimation to make for any of the laboratory sources, whether it's a seal tube microfocus, a rotating anode, or a metal jet.
We no more questions with the chat. I can always ask additional questions, but are you here to ask anything specific?
No, I wanted to talk about our specific instrumentation. But I do have a question. You mentioned earlier the ability to look at the unobstructed beam right in the detector without having a beam stop on it, which is novel since the last time I've been looking at this technology. How did you do that?
Well, we just.
I know it's great.
I mean, the credit goes. So the credit goes to Dectris. They are the manufacturer of the detectors from Switzerland. So these detectors, they're called hybrid pixel detectors. They're basically little photodiodes on a pixel pad that's, in the case of the newest ones, in case of yours, it's 172 by 172 microns squared. And each of those pads has the detector, it's a silicon sensor, and then underneath is all the processing electronics in that pad. So what's really cool about it is that each of those little pads, each of those little sensors can take, in the case of the newest detectors, 10 to the 7 photons per second per pixel and stay linear. So there's no damage and count linearly up to that rate. Well, that's higher than anything we're going to see in the lab.
Phenomenal.
It really is. I mean, I can't. I mean, I am in amazement still. So, but you have to do a few tricks. It's not enough to just take the detector. First we have to take the detector. We have to make it vacuum compatible. So that's something we worked with Dectris, and now it's a standard product that they have. Many of the synchrotrons, I would say, have, or say most of the beam lines now have vacuum compatible detectors for small angle scattering, where they're running up and down the flight path. The next thing you have to do is you have to remove the Mylar window that's in front of the detector. So if you look at your detector, you don't see the sensors, you see this luminized Mylar window. You have to take that off, because if the direct beam hits that window, you're going to see basically wide angle scattering from aluminized mylar, in addition to whatever, whatever the direct beam is and whatever your sample scattering is. So we remove the window on the detector. We put the detector in vacuum, so there's no end window. There's no, Kapton or Kevlar window that gives additional scattering. And then once we do that, we no longer need the beam stop. That detector can withstand direct beam intensities from any laboratory source, certainly a copper source, for literally decades on a single spot. And it's just incredible. You couldn't do this at the synchrotron. The synchrotron is so intense, it would destroy that. It would destroy that pixel. But they're just brilliant detectors. And that's why everybody's using them. You can put in that 10⁷ photons per second per pixel, and have, if somehow you were able to collimate your beam, see nothing. There's no crosstalk with adjacent pixels at all.
So Brian, what you said before with our gear here about measuring the unobstructed beam, putting a stop, putting the sample in to get the absorption, do we still need to be messing with the stop?
Yes, because our detector is not under vacuum.
Exactly.
It's still outside.
It's still outside.
Yeah.
Okay.
It's outside, yeah. So we provide, one of the things that we did was we provided a beam stop that is motorized, so you can move it out of the way, and that's part of the detection process. So the only way to do it is to have the detector in the vacuum chamber. That particular detector is an older one, predated any of the vacuum compatibilities, so that detector will not go into vacuum. And I think we had this discussion early on that, when the day comes, we will need to get another detector, a new detector that is vacuum compatible.
Absolutely.
Okay, thanks. But like Travis, I could ask questions all afternoon too, and I'm not going to do that.
Yeah, and we can have another conversation too. That's fine. This is part of my job. This is what we do. Anything to get more people, just curious about using the instrument, and encouraging people to get on and just try it. A lot of people will, I won't go on too much longer, but a lot of people will worry about, oh, what's my contrast? Will I see anything? Don't worry about it. Just try it. 5 minutes. You'll know if there's something there or not.
It's the first step on that long pathway to buying one.
Yeah. Well, it is, and most people get introduced. I encourage people, if they don't have a system in-house, find somebody who does, or go to a synchrotron. I mean, synchrotrons are amazing places, because even if you have a vanilla flavored sample, if you've never done it before, some of the places, I'm thinking about NSLS2. I mean, they're really great about taking people under their wing and, showing like I just had a conversation today with a synthetic organic chemist, sort of inorganic / organic. And they hadn't done scattering before. They went to NSLS2, and now they are totally addicted to scattering. And the students coming out of the group not only do, fairly heavy duty synthetic work, but then they're also learning how to do the scattering. And that's pretty cool. That's, there's no reason that everybody can't do that.
That's part of the way we behave around here too, enabling people to learn things.
Yes.
Any other questions?
No more questions in the chat, but we haven't. Does anybody have any things they think they might? I mean, if you can create a semblance of a question, I think Scott can turn it into a fantastic answer. So that's the feeling.
No.
Awesome. Sounds like nothing else. So thanks again, Scott. Really appreciate you taking the time to give us the seminar today. I think a lot of people, including myself, learned something, and yeah, come talk to me or Travis if you're on site and have questions about something specific for your research or want to take a look at the system itself.